Good morning or good afternoon, good evening, depending on what time zone you are in. Welcome to the Fairness and Discrimination through the Dual Lenses of Mechanism Design and Machine Learning tutorial. I'm Manish, and together with my co-presenters, Phaedra, Edwin, and Jesse, we're going to be giving you an overview of some of the research and results on fairness and non-discrimination at the interface between mechanism design and machine learning. So we'll be talking primarily about machine learning mechanism design and some combination of the two, maybe even a little bit beyond. And the plan for today is for this session, I'll be discussing some of the results on fairness and discrimination in the context of machine learning. Phaedra will then discuss the same, but in the context of mechanism design. Edwin will walk us through an exercise on resource allocation based on vaccine distribution. And finally, Jesse will close us out with with some of the lessons that the fields have to teach us and to one another, and some critical perspectives as well on these fields. Okay, so the plan for this section for the next 45 minutes to an hour, I'll start out with just a little bit of background about what are the types of applications and systems we're talking about and the concerns that people have raised. And then I'll go into more detail on the machine learning side. We'll talk about some of the basic definitions in the field and some of the sort of basic results and folk wisdom that we've gotten over the last several years from the field, and some relations to applications that we have in mind. And then we'll leave some time for Q&A as well. So broadly speaking, the types of systems that we're talking about can be sort of broadly termed algorithmic decision-making systems. These are decision-making systems that are actually used in a very wide variety of contexts, where decisions are made about people's lives and algorithms have some input or make up some component of that decision-making process. These are having an increasingly high impact on people's lives, and these systems are getting more and more complex as we go. And so there's a push to understand how these tools really impact our society. What changes when we start making decisions via algorithm, and how can we make sure that we have positive impacts on society? Some of the applications that we're thinking about here include lending and sort of credit decisions, algorithms that operate in the gig economy, algorithms that do content recommendation and moderation, and algorithms used in consequential domains like the criminal justice system. And if you've been following over the last several years, there's examples of plenty of cases where people have pointed out instances of bias or discrimination that are occurring in these automated decision-making systems, including in the criminal justice system, in recruiting and hiring, in education. These sorts of examples tell us that we need to be paying more attention to these algorithms and the impact that they have when they get deployed. Now, in a sense, this comes from a sort of a longer history of trying to interrogate the way that technology embeds value. So perhaps the most classical example of this that you'll often see is from 1980, in an article by Langdon Winter, where he details what's called the Robert Moses bridge example. So Robert Moses was responsible for the design and implementation of a lot of the parks and transportation system in the New York City area. And one thing that he did was when he was designing the highways that went out to Long Island, he intentionally built the bridges over those highways to be pretty low. And the goal behind doing that was to prevent buses from being able to get out to Long Island. And what the effect that had was wealthy people could drive their cars out to the beaches in Long Island, but you couldn't have bus routes that would take less wealthy people out to the beaches. So that was sort of a way through technology, certain decisions and values were sort of embedded into the technology. Decades later, Batya Friedman and Helen Nissenbaum discussed how these same sorts of biases can actually manifest in computing systems. So these aren't altogether new problems, but these all point to the need to better understand the relationship between technology and the values that they embed. Now, why does this get much more challenging with these modern algorithmic systems? There's a few reasons why these systems bring new challenges that we perhaps haven't seen before. For one, these systems are to some extent automated. right? As opposed to making concrete decisions like I'm going to build this bridge at a certain height. These systems make a lot of their decisions in a sense on their own, right? We feed them data and they learn from that data, but a priori we can't predict exactly what that system is going to do. They're also dynamic. They can change quite rapidly as conditions on the ground change. So not only do we have to reason about how these systems are going to work today, we also have to reason about how they're going to respond to future changes and sort of future-proof them in a way. They also have to incorporate and respond to human behavior, which is inherently quite unpredictable. So not only do we have to reason about the actions that the system will take, we also have to start thinking about how people are going to interact with it and how people's behavior might change as they are exposed to these algorithmic decision-making systems. So all this to say, these systems are going to raise new challenges for our society. Some of those are moral and political challenges, but some are also technical challenges in a precise sense of the word, in that they will require the development of new technology to address them. So that's part of what we're going to focus on today is what sort of new technology are we developing in response to these new systems, and how do they interact with these political and moral values that we might share. So the first thing that might be useful to talk about when we think about fairness in automated decision-making is, of course, what do we mean when we think about the word fairness, and where do our notions of fairness come from? There isn't a single definition I can give you, and definitely not a single one that we'll all agree on, but I find it instructive to take a quick look at how fairness has been instantiated and operationalized in different places over the years, just to see where these ideas have come from and how people have tried to formalize them in the past. So the list I'll give you is by no means exhaustive, but we'll try to take a look at some formulations of fairness in philosophy, in economics, and in the law. Now, fundamentally, in all of these traditions, fairness is contested. There's no one agreed upon approach or definition that people can provide you. And we shouldn't expect perfect agreement about what is considered fair or not. But this lack of consensus shouldn't prevent us from at least trying to better understand what can be done and how we might go about doing it. So let's start off with a brief look at fairness through the lens of philosophy. So there are two main philosophical lenses through which fairness can be viewed when it comes to algorithmic decision-making. The first is consequentialism, which is concerned with the impacts of the outcomes that a system produces in the world. So essentially, consequentialism tells us that a decision-making system should be evaluated by the outcomes it produces. Now, one major tradition within consequentialism, which many may be familiar with, is utilitarianism, which is the notion that we should make the choice that benefits the most people or brings the biggest net utility increase to the world. Utilitarian isn't the only consequentialist approach. You may also be familiar with prioritarian approaches, which favor increasing the welfare of those who are least well off in society. So those are the utility or the consequentialism type approaches are looking at the outcomes that a system produces. The other main tradition that's of relevance to algorithmic decision-making is deontology, which is concerned with rights and sort of constraining the process by which decisions are made. So for instance, if we as a society think that people have a right to not be judged on a certain attribute, this would be a deontological rule that says don't include this attribute when making an evaluation about a person. Now, this may lead to in aggregate worse outcomes, and perhaps a utilitarian might disagree, but these are types of constraints we might also think to put on algorithmic decision-making systems. And also throughout these slides, I'll try to annotate the bottom with some references for further reading in case you want to know a little bit more about the topic that we don't have time to get into in this particular tutorial. Okay, so we talked a little about philosophical perspectives, and actually these philosophical perspectives have often been operationalized and formalized to some extent in the economics literature, particularly as they pertain to questions of social welfare and resource allocation. A classical example is fair division. We have some resource, it needs to be divided, and we might have some axiomatic formulations of what it means to do so fairly. Economists have also considered questions of how to fairly aggregate people's preferences into making decisions. So your city has a budget that they need to spend. People have preferences as to how that budget gets spent, and social choice theory can help us figure out what is a good way to aggregate those preferences. The last thing we'll consider is the question of discrimination itself. So economists have long considered questions about discrimination. Why do people discriminate? What is the basis for doing so? And what are the impacts of different interventions aimed at minimizing that discrimination, both from empirical and theoretical perspectives. And Phaedra will go into more detail on all of this in the next session as she starts to cover perspectives from economics and mechanism design. The last source of ideas about fairness that I want to briefly discuss is the law. So, the design of these modern algorithmic systems is actually heavily influenced by constraints that are placed by the legal system. So I'll speak primarily about the US legal system for the purpose of this tutorial. A lot of the principles are actually found throughout democracies around the world. So while the law does draw upon these philosophical and economic principles, the law is also sensitive to empirical sociological facts about the world. For instance, you could ask the question, why does the law forbid discrimination based on certain factors, like for instance, race, but not others like height, right? Now, this isn't an arbitrary distinction that the law draws. This is in response to discrimination that occurs and has occurred throughout history, really. So the law isn't simply making arbitrary distinctions, nor is it taking a high-level theoretical perspective. It actually needs to be concerned with the implementation of rules as well. Now, in general, the law doesn't tell us what we explicitly should do. The law is typically set up to prohibit certain actions, but allow for agency within those boundaries. And the final thing that's important to point out is the law also allows for discretion and interpretation. And this can be frustrating to many computer scientists because we're trained, we want hard constraints and we can optimize within those constraints. But we shouldn't view this these sort of standards that are up to discretion and interpretation as a mistake. These are actually intentional. There's actually a longstanding legal notion of the distinction between rules and standards, where rules are hard constraints like a 0.08 blood alcohol limit is the legal limit in many jurisdictions for drinking and driving, as opposed to standards which are often more vague, like a driver should act with reasonable caution. And in fact, when it comes to questions of fairness and discrimination, the law often implements these prohibitions in terms of standards that are up for interpretation as opposed to hard and fast rules. And so what we need to do is be able to design algorithmic decision-making systems that are cognizant of the way that the law works and don't try to impose hard and fast rules when those rules don't exist. So now that we've taken a brief look at where fairness comes from, we can start to consider how these ideas apply to machine learning. The basic question really is what makes decisions fair or discriminatory? And given that we've been studying these questions of fairness for decades or for even centuries, why don't we have all the answers? And there's a lot of ways in which machine learning brings new challenges that we perhaps haven't encountered before. And I'll give you a couple here. One is that machine learning and the implementation of these algorithmic decision-making systems require us to be very precise about what we're doing in a way that we haven't before. So for instance, if previously a body of human decision makers were implementing a decision, they might disagree, they might do have some sort of arbitrariness or randomness in their decision making, but somehow we let that slide because we couldn't actually precisely locate that arbitrariness. But now that we have algorithmic decision making systems, we have to be precise in a way that we never really were able to do before. We can run counterfactual, sort of change some features and see how the decision would change. So these types of we weren't able to do these types of things before, and as a result, we have to operate at a new level of precision. We also see that from theoretical formulations of fairness can be somewhat abstract, right? So some philosophical perspectives will talk about people who are equally qualified or equally deserving in some way, and this works well if we already know who is equally deserving and equally qualified. But in a sense, determining who is qualified is the task that ML is seeking to accomplish. So we don't really have ground truth necessarily by which to evaluate these systems all the time. So as we get into trying to answer some of these questions, it'll be useful to start with some basic definitions that I'll run through here. So in the machine learning literature, things have often been formalized as follows. So people show up to be evaluated in some way. They have features, which we'll call X. There's a thing that we are trying to predict in many of these settings, which I'll call Y. And there's the actual prediction that our system makes, which I'll call Y hat. And so far, this is all pretty standard in a machine learning setup. The thing that might be slightly different if you haven't looked at work in this space before is that there's often assumed to be what's called a sensitive or protected attribute A. In the literature, you'll often see this as race, gender, socioeconomic status, language, for things like that. And the goal of many of these definitions or notions of fairness is to say we shouldn't discriminate on the basis of this sensitive attribute A. So with what can you actually do with these definitions? I'll give you an overview of 3 high-level approaches people have taken in operationalizing principles of fairness in machine learning. And I should stress my goal here is not to be exhaustive. This is just to give us some common language to work with and perhaps try out on various applications. So the 3 high-level approaches we'll cover today are known as individual, group, and counterfactual fairness. So individual fairness is premised on the idea that similar people should be treated similarly. So the idea goes, if 2 people are quite similar, it would be unfair in some sense if they receive vastly different outcomes from our system. Group fairness operationalizes the idea that on average, people of different groups shouldn't experience the decision-making system very differently. Now, what do I mean by experience and how do I quantify that? I've been sort of vague on this slide and I just said, some metric in expectation should be equal for different groups. We'll go into a little bit of detail about how you might actually try to operationalize experience in that sense. And then the final thing that we'll look at will be counterfactual fairness. And counterfactual fairness asks the question, how would things have changed if the sensitive attribute had been different, right? Would this individual's outcome have been significantly different if they had been of a different race or gender? And if so, maybe that's evidence that this decision-making process is unfair. So we'll look at it in a little bit more depth about each of these approaches. And one question I want you to keep in mind here as we do is where might reasonable people disagree, right? If we have differing perspectives on what is considered fair, under these technical definitions, where is that disagreement going to manifest? And so that's something we'll keep returning to as we go through these definitions. Okay, so let's start with individual fairness. Now, individual fairness comes out of a seminal paper by Dwork et al. In 2012 called Fairness Through Awareness. And the premise of that paper was something like the following. Suppose I gave you a distance metric in the feature space. So I could tell you how far apart any 2 individuals were. And then, we have some predictor, y hat, and we'll say it's some function f of x. And finally, suppose we also have some way of measuring distance in the space of outputs. What individual fairness requires is that the distance between if we have 2 individuals, the distance between the outcomes they receive shouldn't be more than the distance between those individuals in feature space. Or put another way, people who are very similar should be getting similar outcomes, right? Now, intuitively, this seems pretty reasonable, right? We think that this says something about our intuitive conception of fairness. It's also technically somewhat feasible, right? You could think of this as essentially a smoothness requirement somehow in the predictors that we make. Okay, so this is a natural formulation of fairness. Now, what are the challenges associated with implementing something like individual fairness? Well, one of the biggest challenges is that we had to assume in the first place that we knew a distance metric in the feature space, right? We knew how similar 2 individuals were. Now, going back to this question of where might people disagree, we might reasonably disagree on which 2 individuals we consider more or less similar. There's some work that seeks to move past this by learning from feedback. So if you have an oracle who's able to tell you, yes, these people are similar, or these people should have gotten, or close enough together that they should have gotten the same decision, we might be able to learn from that sort of oracle style feedback. So there's some work to extend in that direction. The other challenge that we might face is that we often need a smooth output space in order to be able to implement this, right? If we have a strictly binary output space, it might be difficult to, we're always gonna have a case where there's a decision boundary somewhere and someone just above the boundary and someone just below the boundary will look similar in feature space, but will receive very different outcomes. Now, a technical solution to this is often randomization. So instead of making pure binary predictions, I say this person has a 55% chance of getting a positive decision. This person has a 50% chance. Now, this sort of randomization, while it's clean and it works nice from a technical perspective, may often be undesirable from a social perspective, where people may not want their consequential decisions to involve any amount of explicit random. So there may be some trade-offs there as well. Okay, moving on to group fairness. Group fairness, as we said, seeks to equalize some metric across different groups. So examples of which metrics you might seek to equalize include error rates, like false positive rates and false negative rates. So you might think if one group suffers from significantly more false positives or false negatives than another group, this might be evidence of some unfairness. From a mathematical perspective, in terms of the variables we were talking about, you might write this as trying to equalize the expectation of y hat conditioned on y and a. So given that these are essentially what give us the ability to measure false positives and false negatives broken down by these groups. Another thing we might seek to equalize is simply the selection rate for different groups. This is also often known as demographic parity. And this basically says that the pool of people who we select, let's say we're doing like a hiring type application, the pool of people that we select should be demographically representative of the people who we are evaluating. Okay, and formally, what this would look like is simply the expectation of y hat conditioned on a. And a third category of things that we might seek to equalize are metrics about predictive information. So these are some names for this include calibration and positive predictive value. And basically the intuition for these types of measures is that a prediction should mean the same thing regardless of who that prediction is about. So if I give you a prediction about a person, you shouldn't gain any additional information by knowing, say, that person's race. Okay, and formally we might write this as looking at the expectation of y conditioned on y hat and a. So these are a few ways or a few types of metrics you might seek to equalize across groups. Now, how might you actually go about doing this? Again, methodologically, there's a huge variety of ways that people have developed over the last several years. Broadly speaking, there's three main categories of methods. The first is interventions that take place before you learn your classifier. So these sort of pre-processing and representation learning approaches, for instance, representation learning, which comes from a paper by Zemel et al., seeks to take your feature space and transform it into a new feature space that maximizes predictive information while minimizing any correlation with the sensitive attributes. Constrained learning involves adding a constraint or a regularization term at trading time to a classifier in order to encourage or enforce equalizing the metric in question. And finally, post-processing approaches essentially say, build whatever classifier you want, hand me that classifier, and I'll take the outputs and randomize them or tweak them in some way in order to turn it into one that satisfies the desired constraint. So what are the challenges associated with group fairness techniques? One big challenge that you might have is which metric should we seek to equalize? I've given you a number of those possible metrics. It's not clear which one are ones we're trying to equalize and what that actually means in the context that we're working on. This is also a place where people might reasonably disagree on, what do we think is worth equalizing and what do we think are the reasons to do so? You might also have the question, we're operating at the level of averages here, not at the level of individuals. And you could ask the question, are averages even meaningful in this context? So, if you're doing something reasonable for 95% of people, but give really bad outcomes to 5% of them, group fairness notions would struggle to capture this, but you might argue that this is inherently an unfair thing to do. There's also the issue that many of these measures are in some sense manipulable, right? They are measured not just with respect to a classifier, but also with respect to the distribution, the data distribution over which that classifier is evaluated. So for instance, if I'm trying to enforce equal selection rates across different groups, and I find that one group has a much higher selection rate than another, I could just add a lot of unqualified members from that group to the data set and lower their perceived selection rate without actually changing the classifier itself. And finally, it's worth noting that many of these metrics and measures that we've discussed here are actually incompatible with one another. So except under some limited circumstances, it's actually mathematically impossible to simultaneously equalize multiple constraints. Okay, so this is why some of the reasons why group fairness might be challenging to implement in practice. The final set of or approach that we're going to cover today is counterfactual fairness. So again, counterfactual fairness is asking the question, how would the decision change if this protected attribute were changed in some way? And what this requires us to do is to build a causal model over the observable and unobservable features. And within that model, we can now intervene on certain variables and see what changes in terms of the distribution over outcomes. Now, it's important to note here that when we change an attribute, this necessarily involves changing attributes or changing the distribution over attributes that are causally downstream. So for instance, changing someone's, like changing gender might change the distribution over names that you see on that person's resume, for instance. There's also the notion of resolving variables, which are essentially variables that are deemed acceptable to discriminate on. And maybe the clearest example of this comes from this famous case of Simpson's paradox in UC Berkeley graduate admissions, where on average, women were admitted to graduate programs at a lower rate than men. But when they went and looked at individual departments on average tended to actually favor women slightly. And what this happened, or the reason for why this happened, is that women tended to apply to more selective graduate programs, and so they were less likely to be admitted. Now, if you consider your choice of graduate program as a resolving variable, as in this is a variable on which it is justified to discriminate on the basis of, then you would consider these admissions to be counterfactually fair according to this particular definition. So there's some complexity in making these definitions, and not so simple as just building your causal model and then letting the definitions run wild. So what makes counterfactual fairness challenging? Well, one difficulty right off the bat is we have to build causal models, which can be hard to do. Sometimes it's not identifiable exactly what the causal structure is from the data that we might have. And we might reasonably disagree, again, on what the right causal model is for the world that we live in. Also, we might disagree on what makes a pathway justifiable or what the resolving variables should be. This is another place that our human disagreement might enter the process. And finally, there's the question of, is it even meaningful to ask counterfactual questions about immutable characteristics like race or socially constructed characteristics? I don't have time, unfortunately, to get into an in-depth discussion of this, but I'd recommend this paper by Lily Hu and Isa Kohler-Hausman for a more detailed discussion. Okay, so now that we've run through these definitions, I think it might be useful to see how they might actually apply to a particular hypothetical case. So let's say we're in a case where we need to build a resume screening algorithm. So you're working for some company, you have 1,000 applicants a day, and you need to somehow filter this down to 300 or so that your HR department can actually take a look at. So first off, it's easy to see the risks of discrimination here, given all the history of empirical findings on discrimination in resume screening and in hiring more generally. And so you could ask the question, what could our fairness definitions do here? How would they apply? So again, we'll run through these 3 high-level approaches and see what they might tell us. So first of all, what would individual fairness say about our resume screening example? So recall that individual fairness says that similar individuals or similar resumes should get similar outcomes. So what this might mean is if we have 2 resumes that look identical but differ very slightly in GPA, for instance, individual fairness would say that the probability of interviewing these candidates should be similar. Okay, so fairly simple application here. What about group fairness? So to operationalize group fairness principles, we need to pick some metric to equalize across groups. So let's say we take demographic parity as an example. So recall that demographic parity says that the selection rate from one group should be roughly the same as the selection rate from another group. So in this case, we might say that, for instance, the group on the left, Asian applicants should get interviews at the same rates as white applicants, the group on the right. And as you see, 2 out of 6 resumes from both groups are getting the positive decision or getting interviews, and therefore this would be considered fair from this demographic parity perspective. Now, the final example to go through is counterfactual fairness. So recall, counterfactual fairness says that changing a sensitive attribute shouldn't change the outcome. Right now, supposing we start off with my resume on the left and consider the counterfactual where I'm a woman, and you note that maybe in this counterfactual world, my name may have changed, maybe the distribution over names has changed, but it might also change things like where I went to college. For instance, if I were a woman, the probability of me going to a women's college would be higher than it is now. So a counterfactual might have to take into account not just this change, but also the downstream consequences that change might induce. Now, there's a caveat that we have to think about here, which is that what are the resolving variables, or what are the sort of justifiable pathways for discrimination here? For instance, are disparities that arise from the choice of where to go to college a result of personal choices or unfair discrimination and perhaps social factors in the world? And again, this is another location where some subjectivity and disagreement might enter in even constructing a technical definition of what we consider fair. So now that we have some familiarity with these definitions and how they might apply, let's go over some of the basic results in, as maybe you'll call it, folk wisdom that people have accrued in the field over the last several years. The first basic finding to point out is what I'll call fairness through unawareness usually doesn't work. So the most naive solution to this problem of discrimination might just be, well, let's remove all sensitive attributes from our data. If we don't know about them, we can't discriminate. And of course, this won't work. There's always going to be proxies in your data, and information about sensitive attributes will leak one way or another. So simply closing our eyes isn't going to do it. The next finding that's important to keep in mind is that there's no universal solution that we can just, there's no wand we can wave and magically make everything fair. And in fact, it's unlikely to be the case that we'll find a purely mechanical approach that solves this problem without considering what I'll call broadly context. Context matters. The particular application that we have and the concerns at play there will dictate what sort of approach we take, and 2 different contexts might require different approaches. And even within a single context, there might be reasonable disagreement on what we consider fair or normatively desirable. Okay. Next is a slightly more subtle point on looking at estimators and the way that we use them. So you might have a sort of high-level question of, should we even change the way that we do machine learning, or should consumers of machine learning predictions change the way they use those predictions in order to promote goals of fairness, right? And so this question of should we change estimators or how they're used has been considered by a lot of people. Now, mathematically, the arguments that typically get made are that it's in some sense optimal to build estimators that use as much predictive information as possible, and then downstream change how those estimators are used in order to meet whatever policy goals you have. So the references that I've included up here all sort of make the case that the right thing to do is to use all the information you have, build the best predictor you have, and then you can use those predictions however you want and adapt the way that you use them in order to promote goals of fairness. But in practice, this can actually be undesirable for a number of reasons, right? Building optimal predictors often requires directly using sensitive attributes at prediction time, like race or gender or age, for instance. Now, from a legal perspective, this is typically frowned upon or even illegal in a number of contexts. And also normatively, you should ask the question, do we want people to be judged on these demographic characteristics? So this might point to a place where there's a conflict with between what appears to produce the best outcomes from a technical perspective and what is normatively acceptable from society's perspective. Okay, the next point to make is that, broadly speaking, details matter, right? I gave you this toy binary prediction setup where we have features, we have targets of prediction, and we make some predictions and see what happens. But often that abstracts away important contextual details. For instance, is there a known desirable outcome, like in cases of screening in the criminal justice system or in hiring or in education, versus cases where we actually don't know what people want, where we're trying to learn people's preferences as we go. We might think of fairness quite differently in those different contexts. We might also think of fairness differently in cases that are resource constrained versus cases that are not. For instance, in this resume screening application that I gave you, we have I hypothetically assume we have a limited number of HR people who can actually review resumes. And so, every resume we admit means one other resume can't get admitted. So we might, again, think of fairness differently in cases where we have these hard resource constraints. We also should think about details like the legal constraints in the system, because we might have something that seems normatively or intuitively fair to us, but for legal reasons, we could not implement it or could not implement it in certain jurisdictions. There's also the question of, is there a human in the loop, and what sort of agency do they have in the process? So for instance, in many sort of models of joint algorithm and human decision-making, an algorithm screens some people out and forwards everyone else along to be then reviewed by a human. Now, is that the right way, the right model of collaboration? Do our conceptions of fairness change if we know that this is how our algorithms will be used? We should also be asking questions about where data and labels come from, right? Are they coming from some biased human process, and are there known biases in that data? Are they representative of the actual population that we wish to evaluate? Do the labels even mean the thing that we want them to mean? So for example, in the criminal justice system, a lot of tools are built with labels of who ultimately is arrested, as opposed to what they actually want to measure, which is who went on to commit crimes. And so we should recognize that the labels that we receive may not, or are often not, the actual thing that we want to measure. And finally, we should also consider who bears the cost of errors. Is it the individual? Is it society? Is it the decision maker? And how does that balance of who bears the cost of errors going to affect our perceptions of fairness? And the final lesson that I think we should learn from is not to assume Pareto efficiency. Okay? The common argument that you might hear is fairness is in tension with accuracy, or necessarily forces us to make trade-offs and sacrifice accuracy in order to promote goals of fairness. But in fact, we can actually often be quite far from the frontier. There might be a lot of room for gains. For instance, if our notion of accuracy is misspecified in the first place, if we're evaluating a system based on biased data, trying to obtain less biased data might actually be good for both fairness, but also accuracy, given that we now have a better measure of accuracy. And this is one way of viewing this is actually through the lens of a lot of audits that have been done in recent years on things like facial recognition and speech recognition that found that there are accuracy disparities between people of different groups, particularly against darker skinned individuals in facial recognition and against African Americans in speech recognition. And you might look at these and say, well, how could these disparities possibly exist? They don't actually benefit everyone. It's in everybody's incentive to fix them. And yet in practice, we still run into cases where systems are just not designed to work well for everyone. And so this is another place where we have room to make gains that don't come at the expense of anyone. So that's a lot of lessons or results that I've thrown at you. Let's try to make them more concrete and look at how they might apply, again, to our resume screening example. So one of the most important constraints that you might face in an application like resume screening is the legal constraints, right? You might want to implement whatever definition of fairness you have, but ultimately you have to think about whether the law allows you to do that. Again, I'll focus on the US perspective simply. This is because this is where I live and what I study. But some of these principles are, again, generalizable to other contexts. So in the United States, there's a couple broad protections that people have in employment discrimination. One is against disparate treatment, which basically is meant to prevent intentional discrimination. And the most common interpretation of disparate treatment in the context of machine learning is to not include protected attributes in your model. Right? You should not judge someone on the basis of one of these protected attributes, where exactly which protected attributes we're talking about are defined in the law itself. I should say that this is the most common interpretation. It is not the only interpretation, going back to our earlier point about how these things are often not hard and fast rules. The other broad protection that the law offers in the US is against disparate impact, which basically says if there is a significant violation of demographic parity, if the selection rates are very different for different groups, there may be grounds for a discrimination case. So if we were to apply any of our fairness definitions in this context, we'd first have to know how they interact with the law here and make sure we design them in such a way that isn't going to violate people's legal protections. In resume screening, we also have significant constraints on our data. If we think about where this data comes from, for one, we often don't have ground truth on who is a good employee or not, right? Often we're learning from messy, biased signals from human recruiters. Maybe we don't even measure people's actual job performance. All we really measure is whether that person did well on the interview or not. And so those might be the predictions that we're trying to match. We also have one-sided collection of labels, right? We don't get labels from people who got screened out by this resume screener. One thing that might suggest from a technical perspective is you might need constant built-in randomization and exploration in order to learn about people that you thought were unqualified. And there's a line of work on considering questions of fairness in sort of online learning problems. Some of those references I've included at the bottom here. And the last or another limitation on the data we might have is access to people-sensitive attributes. So in most cases, people don't put their gender or race on a resume. And even if we don't actually want to use these attributes in our predictions, it might still make it hard to even audit our own system and understand how we're performing for different groups of people. Another important contextual thing to keep in mind is that there's some level of Pareto inefficiency in these sort of HR tools in general that people have found empirically. Many vendors of these tools actually claim that they can significantly reduce outcome disparities or sort of violations of demographic parity without significantly impacting their accuracy. So on the picture that I've made here, you might go from a tool that has like 58% accuracy, but very different selection rates by demographics, to one that has slightly lower accuracy, but actually roughly the same selection rates for different demographic groups. So in some sense, you could view this as a very low accuracy fairness trade-off if this is how you want to define fairness. It also draws from the idea of like predictive multiplicity that has been recently explored in the literature, where there might be many classifiers you could build that from a performance perspective look quite similar, but actually have very, very different outcomes in terms of who actually gets positive decisions under those classifiers. So maybe the fact that these changes are even possible might again significantly impact the way that we design and build tools. And finally, you might notice that my initial definition of the problem space, right? We have we're building a resume screening tool. Some people get screened in, some people get screened out. That was somewhat limited by the abstraction barriers that I had put up, right? I frame this as a single company making yes/no decisions on resumes. But the real world actually allows for much more complex behavior. So for instance, there are platforms like LinkedIn, Monster, and Career Builder that, in addition to performing a sort of screening and evaluation task, also perform a matching task, right? They might show your profile to employers who they predict you're a good match for. Now, what kind of additional concerns might this raise? And can the framework that we describe, this purely predictive framework, even handle this level of complexity? And in fact, if you think about it, many of the applications we care about require us to go beyond purely predictive aspects, right? In applications like finance, auctions, especially ad auctions, in all over the gig economy, things like ride sharing, we have to make some predictive decisions, but prediction isn't the whole story. These applications might actually raise a number of additional concerns. There might be questions of resource allocation and externalities, right? So there might be fixed resources that we can provide to people in the system, and we have to reason about how giving resources to one person or one group of people might affect others. There might also be externalities in things like ride sharing, where sending a driver to a particular location might then impact the earnings that they're able to get for the rest of their trip or the next few trips. So we have to reason about those externalities and sort of design frameworks that allow us to take them into account. More generally, we have to think about aspects of market design, right? If we're thinking about fairness in ad auctions, we need to think, yes, we have to be able to make good and fair predictions about what ads will be interesting to which people, but we also have to consider the sort of marketplace effects that might arise, where certain people might cost more to advertise to, but that might prevent them from seeing classes of advertisements like job ads or housing ads that they might actually be interested in, but just aren't willing to bid as much. In many applications, we also have to think about the feedback and strategic behavior produced by the systems that we build, where you might design a classifier and think that it's working really well, and come back in a year and find that the people have changed their behavior in response to it. And you might have to build systems that actually take that into account right from the beginning. And also, many of these applications that we care about aren't single, one-shot decision problems. They repeat over time. They have many users that keep returning to the platforms. And we have to reason about the long-term effects that will be produced by any intervention that we use. So from all this, what we should take away is that in addition to these ideas about fairness and discrimination in machine learning, we also need to bring to bear tools from economics and mechanism design and see how we can incorporate them to design these more complex systems. And that's what Phaedra will be discussing in the next session. Thanks for your time, and happy to take any questions now.